You're welcome to day 30 of 50 days of tutelage. And in today's class, I'll be teaching you about electrochemistry. I'm going to be walking you through the concept of electrolyte, to the concept of electrolysis, electrolytic cell versus electrochemical cell. And I'm going to be teaching you about some Faraday's law as well and some application of electrolysis. So let's get right into it. One thing we are very, very familiar with is we have always talked about conductors. And what are conductors? They are metals or sometimes graphite that conduct electricity. They help the passage of electricity through from one point to another. So conductors are carriers of electricity. And how do they do this? They do their conduction by free electrons. They do their conduction by free electrons. So that this is what they use to conduct electricity from one place to another. And generally, all metals are conductors. And some things that are not metals that are conductors, like graphite, they are also conductors as well. But what happens is that there's no chemical change in them. All they do is that they just conduct electricity and through the process of what? Using free electrons. And also in the process, their conductivity, when you increase temperature, their conductivity is going to lower, is going to decrease. So therefore, increase in temperature decreases the conductivity of conductors. But electrolyte, which is actually what I'm going to be discussing majorly in this particular class, I'm not interested in conductors. I just want to paint a picture in your head first. So my major concern for this class are the electrolytes. So what are electrolytes? Electrolytes are actually also trying to conduct electricity, just like conductors. But in this case, the electrolytes actually, now conductors mostly they are solids. Yes, they are solids. So, but the moment you begin to have something that is conducting electricity and you have them in either molten state or you have them in aqueous state, either molten state or in aqueous state, then what you are looking at electrolytes actually. So electrolytes, rather than conducting with free electrons, instead what is responsible is for their conductivity are actually the free ions. That is why you have to have them in their molten state or in the aqueous state. So if you say, let's say something like NaCl now, NaCl, it has to be in its molten state or in its aqueous state before it can serve as an electrolyte. And in that situation, according to Arrhenius' theory of Arrhenius' ionic theory, this NaCl will exist as Na plus and Cl minus. So you can pick any other form of electrolyte as well. This is how they will exist. And this is the molten and the aqueous state. We have free ions, and these are the ones responsible for carrying electricity around. So you can tell the difference between electrolytes and conductors like that. Conductors mostly solids, and then they do so, they carry electricity through the free electrons that they possess. But for electrolytes, what do they use? What do they use? They use free ions, and they are either in their molten state or they are in their what? Aqueous state. So that leads me back to electrolytes. So electrolyte, like I've explained, I've given you example already. You have NaCl, you have HCl, you have NaOH. We have the strong one actually, and we have the weak ones. But I'm not really going to be discussing much about those ones. Now, electrolytes, a proper definition to give electrolytes, they are compounds that conduct electricity in molten or aqueous state, and they undergo decomposition in that process. So this decomposition, I'm going to be giving you a lot of details about it as we continue in the class. So take note, they conduct electricity in molten or aqueous state, and they get decomposed by electricity in the process. So what is now electrolysis? What is electrolysis? What is electrolysis? Electrolysis is simply the breaking down of electrolyte through the passage of electricity. So when you supply, so if you have a container and in this container you have electrolyte in it, this electrolyte should be in molten state or should be in aqueous state. Once you supply current to it, this guy will get decomposed and a lot of things will happen actually. So electrolysis is just the process through which electrolytes get decomposed based on the passage of current. That's basically what electrolysis is. And before this can happen, there's a setup we are actually always considering, and the setup is the electrode. We have the electrode, we have the electrolytic cell. So the electrolytic cell, first of all, you have something like an aqueous solution or a molten solution, whichever one. So for now, I'm going to be using them interchangeably until I want to say different thing about them. Then in that place, you also have your electrode. You have your electrode. So let this be electrode 1 and let this be electrode 2. So now in this place, one electrode will be your cathode and one will be your anode. But I'm not going to name them yet. I'm going to explain everything that goes on, why we call one cathode and why we call the other anode. I'm going to explain everything before I name them. So the first thing that happens is that when electricity is going to be supplied into this place, I've told you that this electrolyte, they exist as free ions in this place. So therefore, you have something like X plus and Y minus. So positive ions and negative ions. So during electrolysis, when you want to supply current into this place, current is always being brought into this system through what we call the anode. Current is brought into this system through what we call the anode, and this anode is also connected to the positive terminal of a battery. So current is always going to be brought into this place through the what? Through the anode. And and the anode is also connected to the positive terminal of the battery. So therefore, this is our anode. And we're going to take note of the things that happen at the anode very, very soon. So if this is the anode, what exactly are the things that will go on at the anode? By the way, the anode is positively charged. So it's connected to the positive terminal of the battery, so it's positively charged. So the other one is the cathode, which is actually negatively charged. So this is the cathode. And through this naming now that we have done now, what happens to this positive guy? What happens to this negative guy? So you notice that from law of attraction, negative will attract positive. Positive will attract negative. That's the way it goes. So therefore, who is going to go to the anode is going to be Y minus, and who is going to go to the cathode is going to be X plus. That is why the positive guys, we call them the cations, and the negative guys, we call them the what? The anions. We call them the anions. So ions that are positive are called cations, and ions that are negative are called anions. So what will now happen to them when they go to this place? One thing that happens to them is that they can be deposited at the cathode or they can be deposited at the anode, depending on whatever is going on. I'm going to explain the detail of everything here. But here's what we notice here that will happen. At the cathode, what usually happens there is reduction. And at the anode, what usually happens there, that's not the correct spelling of anode. At the anode, what usually happens there is oxidation. So you can take note of this. Cathode reduction, and anode oxidation. Cathode reduction and anode oxidation. If you remember from the previous class, I'd already explained to you what reduction is and what oxidation is. And I explained this using the concept of losing and gaining of electrons. So I said if you lose electron, that is oxidation. And if you gain electron, that is what? Reduction. So let's see what is going on here. When you have a negative guy goes into the anode, the negative guy means that it has excess electrons. And so therefore, it's going to actually lose its electron in that place. And when it loses its electron, it can become Y. Because when you have a negatively charged ion, in an anion rather, it means that this guy has excess electrons on it. I've explained this in the previous class, how ions are formed. But so therefore, if it is losing electron, that means that it is going through the process of oxidation. And also, it means that it's going from the state of negative oxidation state to zero oxidation state. That's increase in oxidation state. So therefore, you have oxidation. But in the case of the cathode, what happens to the cathode is that it is the positive guy that migrates to the cathode, And what is going to happen is that from X plus, it can become X. And if it is X plus, it means that it is actually deficient. It has electron deficiency. And for it to actually become this X, it needs to gain electron back. So gaining of electron is happening at the cathode. So therefore, that defines what? That defines reduction. So take note, every single time, cathode, what usually goes on there is reduction, while at the anode, what usually goes on there is oxidation. So that is the basic preliminary explanation of what really goes on during electrolysis. But however, we're going to analyze each of these electrolyses one after the other. The first one I'm going to analyze is, I'm going to separate them into two. We have electrolysis of molten electrolyte, and we have electrolysis of aqueous. We have electrolysis of aqueous electrolyte. You see, if you're dealing with molten electrolyte, it is very, very simple and straightforward. So for instance, I'd already given you NaCl earlier. NaCl in the molten state, the only thing you have to consider and worry about, they are Na plus and Cl minus. So Na plus will go to the what? Cathode, and chlorine will go to the what? Will go to the anode. And so what will happen at the cathode is that you have Na plus, which will become Na by what? By gaining one electron. In the case of chlorine, chlorine is actually going to become chlorine gas. So you balance it atomically first. So you put 2 here. So chlorine is balanced. So you have 2 and -2 here, and you have 0 here. So like I told you, I already taught you in the previous class how to balance ionic equation. All you have to do is to add 2 electrons here. So therefore, at the cathode, this is what happened. This guy is deposited. Sodium metal is deposited at the cathode. But at the anode, chlorine gas is liberated at the anode through the what? Through the loss of electron. So that is exactly what happens to molten. So anytime you pick any molten electrolyte, this is what will happen. Just separate them into their positive and negative one. For the positive one, it most likely will be a metal being deposited. For the negative one, it most likely will be a gas being released in the process. So straightforward. However, when it comes to aqueous electrolyte, for instance, let's even use NaCl as well. You have Na and you have Na plus and you have Cl minus. But because it is aqueous, that means that there is the presence of water. So water is also split into these constituents. You have H plus and you have the OH minus. So therefore, you have to always decide which one is going to take the upper hand at the cathode. That is, which one is what is going to happen at the cathode based on this Na plus or H plus. Which one will you choose? And you have to choose between Cl minus and OH minus as well. So to be able to do this properly, there are 3 things that govern them. There are 3 things that govern them. And these 3 things, number 1 is the position in the electrochemical series. Position in the electrochemical series. So when you look at your electrochemical series and you realize that this one, if you have to choose this one, which one will undergo anything during the electrolysis now, you have to choose the one that is actually lower in the electrochemical series. So, and in this case, which one is lower in the electrochemical series is hydrogen ion. You need to go and check your electrochemical series and then make sure you memorize as much as possible from there. So H plus is going to be the one that will be deposited at the cathode in this place now. So therefore, you have H plus going to the cathode. If H plus is going to the cathode, it's going to gain electron there and become H2. So that means that this should have been this. You understand? So I'm just trying to explain. So therefore, at the cathode, hydrogen gas is going to be what? Is going to be liberated. Now, oftentimes, when it comes to this Cl minus and what? And OH minus, OH minus in the activities in the electrochemical series, OH minus will be below. So therefore, in that case, oxygen gas is going to be liberated. I've also explained to you how you balance all these chemical equations. So now, I know I've told you that you balance oxygen with water and then you try to balance everything from both sides and all of those things. So I'm not going to be going into that detail. I've already explained them in the previous class. So take note, that's the first thing. Whoever is lower in the electrochemical series will be preferentially discharged. However, this is only going to be so if you have what we call inert electrodes. So this preferential discharge should be considered only if you have inert electrode. What do you mean by inert electrode? That is, electrodes that are not active. They cannot participate in the whole electrolysis process. So this example are your platinum and graphite. Examples are your platinum and graphite. So these are inert electrode. And because they are inert electrode, then you can consider preferential discharge. But we also have what we call concentration of ions. I've discussed the first one now. The second one is what we call the concentration of ions. Now, this concentration of ions, it actually only affects Cl minus, Br minus, and I minus. That is your halogens, your halo ions. These are the things that it affects, which implies that if you are dealing with concentrated, so if I want to do for concentrated NaCl now, conc NaCl, then the whole electrolysis process changes. Initially, I already told you that what happened is that OH minus will be the one that will go through the process, and then from there you have like oxygen gas being liberated. But in this case, in fact, I think I should actually write that so that we can properly understand this. So you have your OH minus, and then you have so if you do this very well, you're going to have like H2O, then you're going to have oxygen gas being liberated, and then if you have to balance everything, so you have 2 here. Oxygen is how many? So that should be 4 rather. So that should be 4. So that means that you have 4 electrons here as well. So in this place, oxygen gas is being liberated. Oxygen gas is being liberated here. But in the case of concentrated NaCl, so the same separation, you have Na plus and you have H plus. Then you have Cl minus and you have OH minus. Now, this will happen just the way it usually happens. But because this is conc NaCl brine, you have to consider the discharge of any of these guys. So if it is NaCl, NaBr, or NaI, it's going to be one of these ions that will be preferentially discharged. So relative concentration of ions is only going to affect when you have halo ions. That is, you have any of the chlorine, bromine, or iodine. Take note of that. If it is none of these, if it is oxyanions, like for instance, let's say what you had was Na2SO4. So you have Na plus and SO4 2 minus. Even if it is concentrated, it does not matter. It will still go through the normal process. You check your activity series and then you see which one is below, and that will be what will be preferentially discharged. So, but in the case of concentrated NaCl, Cl minus will be the one to be discharged now. So at the anode, you are going to have Cl minus, then it will give Cl chlorine gas, so 2 is here, then you have what? Plus 2 electrons. So there's loss of electron like that, and you can see that oxidation would have taken place. Chlorine moving from chlorine Cl minus to what? To chlorine gas, and that is oxidation. So take note of that very well. That's the second thing. And the third one is actually the nature of electrode. The third one is the nature of the electrode that is being used. So I said earlier that there are some electrodes that are inactive, they are inert, but there are some electrodes that are actually active. They participate in this electrolysis process. And this whole participation can be splitted majorly into 2 parts. But I'm going to be discussing one part majorly. If you have the inactive ones, you follow the same process. So when you have inert, you either consider preferential discharge based on electrochemical series, or you consider concentration if you have any of the halo ions present. So if it is inert. But what if it is active? For instance, you are using an electrode, and in this electrode, maybe you are using something like a metal. You can use copper. You can use silver. All these silver, copper, and the like, they are actually active electrodes. And so what is going to happen is that in the process, if you are doing the electrolysis of, let's say, a particular salt now, Let's say the salt is aqueous silver nitrate, and your electrodes are also made of silver. So electrolysis of silver nitrate using silver electrodes. What is going to happen is that, of course, one of these is going to be your anode and the other is going to be your cathode. So what is affected for this condition, that is nature of electrode, is going to be the anode. Is going to be the anode. The cathode is not going to be affected. And from what you know, the things that will vibrate to the cathode, they will be Ag plus and H plus. So you can use your electrochemical series to know which one is going to be discharged there. But in this place, you have migration of NO3 minus, and you also have OH minus being present here as well. So in that situation, normally we should go ahead and say, oh, which one is below in the electrochemical series and discharge it preferentially. But because this silver is actually an active metal, none of these two would actually be considered. You will not consider any of the twos. So what do? Instead, silver is going to dissolve into solution. And when I say dissolve into solution, it means like mass of this guy is going to reduce. Mass of the that is the content of the anode is going to reduce, because maybe part of it is going to dissolve into the solution. And when I say dissolve and the mass is reduced, I'm not saying that reduction is actually taking place. Let me show you what is going on. This is silver metal. So Ag, when it dissolves into solution, based on Arrhenius theory, it's going to actually become a positive ion. And what does that imply? It means that it has actually lose one electron. So loss of electron will make it to become Ag plus. Therefore, that means that you have negative electron. So, but the way we usually write it is Ag. So you have Ag plus plus an electron here. And from what you have known now, since this is a loss of electron, that is also defining oxidation. So you can see that at the anode, your oxidation still takes place. So please don't get it twisted at all. Your oxidation still takes place at the anode. In this case, what is just happening is that nothing is deposited. Instead, part of the anode itself dissolve into solution. And what is going to cause that to happen is that there can be increase in the concentration of Ag plus in solution. There can be increase in the concentration of Ag plus in the solution. So I'm not actually interested in giving too much analysis about that. And the third thing, when it comes to nature of when it comes to the kind of electrode that we're using, the third thing is whenever you are using mercury as the cathode. When mercury is being used as the cathode. So if you're doing an electrolysis, you have this, so you have mercury here and you have mercury here. So if this is the cathode and this is the anode, so when you use mercury as the cathode and you are doing the electrolysis of concentrated NaCl, so what is going to happen is that, normally in this case, Na plus and concentrated aqueous NaCl, actually, Na plus and H plus will go to the cathode, and then this guy, OH minus and Cl minus, will go to the anode instead. So from what we know, H plus is going to be discharged at the cathode because it is lower in the electrochemical series. But because mercury cathode is the one that is being used, it's going to be difficult for H plus to be discharged. And that is because hydrogen gas will create a higher voltage, a kind of higher over voltage. And so therefore, what will be discharged instead will be Na plus. So what I'm saying is that normally H plus should be discharged. But because we are using a mercury cathode, so this one now, this third thing I just stated now, the third thing is about use of mercury as the cathode. So this takes place at the cathode. Hydrogen ion will not be discharged in this situation. Instead, what will be discharged preferentially is going to be Na plus, even though it is above hydrogen in the electrochemical series. And that is it about electrolysis of all these things. So I believe you can practice more on your own. The next thing we want to talk about is Faraday's law of electrolysis. Faraday's law of electrolysis. Now we have two major laws of electrolysis from Faraday, I'm not going to be doing much of calculation in this class. I'm just going to explain what it is. What it says is that the mass of anything deposited during electrolysis, so maybe it is discharged, deposited, liberated. I've explained all those things. So it can be, something can be deposited, so a gas can be liberated, and all of those things. The mass of this substance is actually proportional to the quantity of electricity that is causing this decomposition in the first place. And so if you introduce the equal to sign, you have M equals ZQ. Z is called the electrochemical equivalence, and Q, you remember, Q equals IT. I is the current and T is the time. So you have M equals ZIT. So this is what the first Faraday's law of electrolysis is talking about. And then for what's it called? For the second law, is basically talking about the fact that number of mole is inversely proportional to the charge. So when you have like two electrolyte connected in series, and then you have a kind of amount of electricity passing through them, number of mole is inversely proportional to charges. I don't want to go into too much calculation for this video because, like I said, I don't want these classes to be longer. This is just like touching the rudimentary and then explaining the basic concept about it. Now we have the application of electrolysis. Earlier, I was talking about this nature of electrode, and I was talking about active electrodes. This active electrode thing, we actually use it. It's actually very, very useful in the application of electrolysis. One of them is actually the process of electroplating. Electroplating. And so, quickly, I'm going to explain. So, to do electroplating, the substance I want to electroplate, I'm going to place it here. Where is that? I'm going to place it at the cathode. Now, whatever I want to electroplate it with, let's say I want to do silver plating now. Or since I think I've used silver earlier, let's do copper plating. Now, I'm just saying, or you want to do zinc plating, whatever one you want to do, that implies that my electrode has to be made of zinc as well. I want to do zinc plating. Then my solution, my electrolyte, has to be a salt of zinc. So it can be ZnSO4. And from what you have already learned, when you have active metals like this, and this is your anode, what will happen is that what? This zinc will dissolve into solution. And because zinc will dissolve into solution, it's going to increase the concentration of zinc, Zn2 plus, and that Zn2 plus will migrate to the cathode. When it migrates to the cathode, the substance that is to be electroplated is now going to be coated, because now zinc, from Zn2 plus, you have zinc now. So this zinc is going to now be used to coat the surface of the substance that is already at the cathode. And that is basically what electroplating is all about. So follow the process. We also use it also in purification of metals as well. It's also the same process. For instance, if this has impurity, so I'm going to choose, let's say I want to purify copper now. So I'm going to have copper here, I'm going to have copper here. This copper at the anode is going to be the impure copper, and this copper at the cathode is going to be the pure one. From what you know, I'm going to use a solution. Let me use, let's say, CuNO3 now. I'm just using random ones. It's a salt of copper. So what is going to happen in this place is that copper is going to dissolve into solution. But as it is dissolving, it is actually dissolving with its impurity. And this impurity can be collected as a sludge. So the impurities can be collected as a sludge. And therefore, copper Cu2 plus will now migrate to this pure one, and then you can now extract it as an actual copper metal. So those are the application of electrolysis. Now let's go to the electrochemical cell. For this electrochemical cell, I'm just going to describe what they are, and I'm going to give you the difference between them and the electrolysis. The electrolytic cell. Then that will be the end for the class, because the class is already getting too long. Now, this is what usually happens. There's what we call half cell. So we have this. In this place, I have, let's say, a salt of zinc. And in this place, let's say I have a salt of copper. Then I dip into this place. I dip a zinc plate here, and I dip into this place, I dip a copper electrode here. So what is going to happen in this place is that there's going to be a form of connection. It's going to be a form of connection. And in this place where there is connection, let me actually break that up. There is a load. There is a load here. And this load, what is going to happen is that in the electrochemical cell, electrolytic cell, like I've said, you are passing the current from outside. So the current is coming into the solution to do a form of decomposition. But in this case, what is actually happening is that you are actually using them to supply the electricity to this external load here. Therefore, what is going to happen is that there's going to be a kind of reaction that goes on in this place, and electron is actually being released. So what usually happens is that between this zinc and copper, one of them will do the releasing of electron. And for one of them to do the releasing of electron, don't forget the things that we have said earlier. For the electrolytic cell, anions go to the anode. The anode is actually negatively charged. The anode is positively charged for electrolytic cell. And then the cathode is negatively charged. So anions are negatively charged. They go to the anode, which is positively charged. But in the case of this electrochemical cell, now I want you to pay attention to something. This guy, based on the electrochemical series, zinc is actually above copper in the electrochemical series. And you see, once one is above each other, then there is a kind of ease with which they lose electron. So the ones above find it easier to lose electron than the ones below in the electrochemical series. So that implies that for guys like potassium, it is very, very easy for potassium, which is at the top in the electrochemical series. It is very easy for potassium to lose electron. But you see, as you begin to go from potassium downward, then you begin to meet people that are reluctant to lose their electron. So therefore, when you have a tussle between zinc and copper, who should lose electron? Then zinc will readily lose its electron than copper, because copper is below it in the electrochemical series. So therefore, this guy is the one losing electron in this place. And this one is the one gaining what? Electron. So what does that tell you? First of all, because of this electron-rich region, this guy is going to be electron-rich region. Therefore, this guy is going to be your negatively charged electrode. Take note of it though. And this guy is going to be your positively charged electrode. So I'm using electron now to determine their charge. This zinc will be the one losing the electron. So therefore, this side is going to be the negatively charged electrode. And this automatically becomes the what? Positively charged electrode. You can see that this is contrary to what we did in electrolytic cell. For electrolytic cell, no, I've not even mentioned anything yet, so let me not jump too much. So let's now see what is happening. From what you understand, there is this thing called CROW, which I've explained earlier in the class. At the cathode, reduction take place. At the anode, oxidation take place. So which one will be our anode here? Which one will be our cathode? From this place, there is loss of electron. And I told you that once there is loss of electron, there is oxidation. So therefore, this zinc will be the anode. And then when there is gain of electron, there is reduction. So therefore, this copper is going to be our cathode. So what you notice now is that anode for electrochemical cell is actually negative. That is for electrochemical. But when you have the electrolytic cell, anode is positive when we add the electrolytic cell. And in the case of cathode, for this electrochemical cell, the cathode is the positive guy. But in this case, the cathode is the negative guy. So follow the process. I'm going to go through them again, one after the other. Zinc and copper. Which one will readily lose electron? Zinc, because it is above copper in the electrochemical series. And because of that, since it is losing electron, it is going to be the negatively charged terminal. So therefore, this guy will be the positively charged terminal. And because of loss of electron, this signifies oxidation. And if it signifies oxidation, what happens, where do we have oxidation happening? Oxidation usually happens at the anode. So therefore, this guy is going to be our anode. And that is the major difference between electrochemical cell and electrolytic cell. Another major difference, like I've explained also, is that this one, electrochemical cell, produces the current. But for electrolytic cell, the current enters it and produces the reaction. So current produces reaction for electrolytic cell that we discussed earlier. But for this one, reaction produces what? Current. So there's a flow of current due to the what? Chemical reaction. And that's basically what electrochemistry is all about. Of course, this is not everything. This is just to lay a proper foundation to better understand it. So now you can go on your own and read further, and you understand most of the things that you'll be reading. If you've enjoyed the class so far, don't forget to like and subscribe to the channel as well. I'll see you in the next one.